The mix size placement is best solved by a global analytical placer, which optimizes wireless and density constraints simultaneously as a nonlinear optimization problem, where the constraints are translated into the objective with Lagrange relaxation. This problem is then solved by gradient descent. DreamPlace accelerated the ePlace-replace algorithm on GPUs. While DreamPlace excels at solving the optimization problem very fast, it also treats macros and standard cell in the same way, which causes many macro legalization issues. Also, the chosen DreamPlace parameters and random seeding heavily influence the optimization convergence and final objective value. To solve these limitations, we propose AutoDMP, which aims at automating DreamPlace to generate quickly, diverse, and high-quality macro placement. We offer extensions to DreamPlace to fix legalization issues and expand the macro placement design space. The DreamPlace parameter space is explored efficiently using multi-objective Bayesian optimization. We propose PPA proxies to judge the quality of a macro placement. We will extract these proxies after legalization and detailed placement performed with ABCDPlace. The rectilinear Steiner minimum tree is used to estimate loosely the routed wire length. We also use the cell density target used during the global placement as a proxy because a smaller density can help timing and congestion. Finally, we use congestion extracted from the rectangular uniform wire density RUDI map as our last PPA proxy. We propose to weigh the smooth half-perimeter wire length HPWL used during global placement to improve its correlation with the ASMT. Secondly, because the macro orientations are fixed in DreamPlace, this can be suboptimal after global placement. So we use a greedy macro flipping technique to further improve wire length. Because modern designs have many macros that can be placed anywhere in the floor plan area with mixed size placement, we model inside RUDI the limited routing resources over them. Because the RUDI map does not account for the fact that routing can be alleviated in neighborhood G cells, we smooth it by applying a Gaussian blur kernel. We estimate the congestion score as an average of the congestion of the top 10% of most congested bins. I present the DreamPlace parameter we will be tuning to explore the design space. This includes the base DreamPlace parameters, such as the density target, optimization parameters such as the one dictating the updates of the Lagrange multiplier and of the smooth HPWL factor. We also introduce new parameters, the initial position and macro halos, that are used to increase the diversity of achievable placements and fix macro legalization issues. All the selected parameters impact the optimization quality. Note the question is how to tune all these parameters to obtain macro placements that are good for the proposed PPA proxies. The more straightforward approach is to translate these different objectives into a single scalar cost and optimize for that cost. However, it is not clear how the various objectives will be weighted. Thus, we propose to use a proper multi-objective method that models the Pareto front directly. We select the multi-objective tree structure Paulson estimator. It is a Bayesian method that builds two internal distributions, one for the good and one for the bad samples. The samples are classified based on their position relative to the currently estimated Pareto front. The MOTP then uses these internal models to make new samples more likely to be good. Running the EDA tool to evaluate all placement samples accurately is impossible. We thus propose a two-step approach. The MOTP tunes the DreamPlace parameters to explore the placement space. Then we select the most promising candidates landing on the Pareto front of the PPA proxies for EDA tool evaluation. However, as there might be many Pareto optimal points, some of which might also correspond to similar placement, we reduce them using k-means clustering and select one representative per cluster. The Bayesian optimization with MOTP is conducted on an NVIDIA DGX station with 4 A100 GPUs. We run 16 jobs in parallel on the 4 GPUs, and we will be gathering 1,000 placement samples per benchmark design. AutoGMP is very scalable. For example, tuning a large design with 2.7 million cells and 320 macros takes about 3 hours. After MOTP, we only select 5 representatives with k-means clustering and run a traditional post-place EDA flow on a CPU server. To assess the viability of our approach, we test it with the open source Tylos EDA flow and macro placement benchmark. We integrate AutoDMP in that flow in 2 ways. We either keep only the macros and continue the rest of the flow normally with power delivery network planning and routing, and full place opt. Or we can keep both the macro and the standard cell placement from AutoDMP, but perform only an incremental place opt that refines the placement and perform timing optimization. Here are the post-Wood PPA results, normalized with respect to the results of the reference flow. Positive values indicate better outcomes for AutoDMP. We get very good PPA results across the benchmarks for both macros only and macros plus standard cell choices. In conclusion, we propose an open source methodology that builds on the GPU accelerated DreamPlace to explore the mixed site placement space. We enhance DreamPlace to fix macro legalization issue and expand the design space. We use multi-objective Bayesian optimization driven by high-level PPA proxy to efficiently explore the design space. Our AutoGMP methodology has good potential regarding PPA on the Tylos benchmark. However, there's still future work to test it on more complex benchmarks. Still, the scalability of the approach can open doors beyond PPA optimization.